everybody, and welcome to today's webinar on power transformer testing using STS 5000. Today, we will be talking about short introduction to STS 5000 and its accessories, so that will be the first part. Then we'll discuss the turn ratio test. After that, winding resistance test. And because they are similar, after winding resistance, we will talk about on-load tap changer dynamic resistance test. Short circuit impedance will be the next topic, after which we will follow by frequency response to stray losses, and then no load test will be our topic after frequency response to stray losses. Topic number 8 will be SFRA or sweep frequency response analysis. We will also have a short reflection on tan delta test. We had two webinars on tan delta, so we will not talk a lot about tan delta today, because we suppose that we covered it, and in the future we can cover it again if you think that that might be a good idea. And the last thing we will mention is demagnetization. So let us start and say that here you can see all of the, let's say not all, but most popular accessories of STS 5000. In the subsequent slides, you will see the characteristics of STS per se, but here you can see some things which can make the testing faster, or without which accessories you cannot execute the test. So you will see later, because it will be shown at the beginning. So when you do, for example, winding resistance or ratio test, if you own an STCS or STCS Plus, you can do it much quicker. But if you want to do demagnetization, you cannot do demagnetization without STDE. The same with tan delta. TD5000 is necessary to do a tan delta test. So let us talk a little bit about the main features of STS 5000. Quickly, the maximum current on the device would be 800 amps AC and 400 amps DC. With the options of booster, you can go up to 2, 3, or 5,000 amps. And just to show you, this would be your booster. On the device itself can generate up to 2 kilovolts. 2 kilovolts is the maximum voltage that this device without any accessory can generate. And we also have low current and low voltage AC/DC generation up to 140 volts and 6 amps. For example, this will be used for your winding resistance test, while this will be used for your short circuit impedance test. The device itself has 4 measurement inputs. You can measure up to 10 amps AC or DC. It can measure up to 300 volts AC or DC, up to 3 volts, and up to 10 volts only DC. So let's say we have 4 inputs. The power of the generator, the power of the transformer inside is nominally 4,800 VAs. And you can see that when we generate 800 amps, this is the power. For 25 seconds, we can generate that. With the booster, we can generate higher currents for this much time. For example, you can generate 5,000 amps for 10 seconds. 400 amps DC can be generated for 140 seconds, which is more than enough to measure usually the resistance. And AC voltage can be generated to 2000 volts, can be generated for 60 seconds if you're generating a higher current. If the current is lower, then you can do it indefinitely. And these are the powers of low current and low voltage outputs. What is important to mention is the accuracy, which is approximately 0.2% for most of the outputs, which is quite high, and the frequency ranges from 15 to 500 hertz. For TD, which is used for no load and for tan delta test, you can go from 1 hertz up to 500 hertz, which gives you a lot of options to see what is your tan delta value. And when we talk about accuracy of measurement, it is more or less around 0.1%, which is quite high for a device which is essentially a primary source. And you can see also that the timer, for example, if you want to measure time, has even higher accuracy. Phase angle measurement has 0.1 degrees. Ratio measurement up to 10,000 is, or 9,999, 0.15, and resistance is about 0.5%. To give you an idea what the device would look like if you're standing in front of it, and I'm sure many of you have already used it, you have your main screen, which is used by turning this knob here. There is an on and off button, programmable function keys, which you can see on the side, start and stop button, emergency button, and also high voltage keys. These are the measurement inputs: 3 volts, 300 volts, 10 amps, 10 volts DC, and these are generations. You see that in some cases we also have the fuses which are outside, so if they burn but for any reason, you can change them quickly. Also, I want to turn your attention to the fact that here you have yellow, and here you also have yellow frame, and here you also have yellow frame. Yellow in this case means measurement, acquisition, while red, as you can see here, and you will also be able to see on the subsequent slides, means generation. So we generate from here and we measure here. This is binary input, where you measure time, and here you have LEDs which signify which output, high current or high voltage output, which are on the side, is used. So again, here you can see red frame, which means generation, red frame, generation, and here is where you connect some accessories. This is where they get their power from. So for example, TD or BUX. So this would be your side of the panel, which can generate high currents and high voltages. You also have very important ground connection, fuses, which you can reset in case you have a surge. And the other side, you have communication. This is what communicates with some of the accessories like TD and STCS. Here you can put in your USB stick to save results or to upgrade the device. This is where the communication through Ethernet with the computer is done. And here we have safety features, warning rotary light, and remote start. So these are the options of STS. And I don't want to spend too much time talking about this because otherwise we will not have time to talk about test itself. But I'm still going to mention that this is what your screen would look like. So you do have the option when you turn on the device to choose the group of application which you will use, or to be more exact, to choose the asset which you guys will be testing. Is it a current transformer? Is it a voltage transformer? Or is it a power transformer? Today we'll talk about power transformer. You can also test some aspects of circuit breaker, also resistances for which you would need some accessories, and control and measurement is an option for you to do manual generation or manual measurement. So you can choose the outputs and inputs any way you like to execute a certain function. Connecting TD5000 to do a tan delta would render this axis to become green, and here are the settings. An important thing to mention is that you can use a test plan. Test plan is a very useful feature in which means that you can create, before you start the test, all the possible tests which you will be doing, and simply because of that, you are able to easily repeat those tests whenever you have to test another power transformer. So it's a good idea to create a list of tests here, as we did for example, in this case, a current transformer, and just to run it on a power transformer every time when you are doing your test. Now, this is a slide I actually borrowed from my colleague Marco Piga, and this is he found fantastic examples. Why do we test power transformer? If you just go to YouTube and type transformer explosion, you will see things like this, or like this, or like this. And let's say that we don't want to have this as our reality. So in answering the question, why does our transformer fail, we see that the lack of maintenance is actually the biggest cause. Apart from that, we have aging, electrical failure, overloading, quality of equipment, extreme weather, mechanical failure, etc., etc. But let's say that lack of maintenance, aging, can easily be covered, which accounts for about 40%, can easily be covered by maintenance. And for maintenance, you will need a device, you will need to test your power transformer, and for that you can use STS 5000. Looking this from another point of view is telling us actually why do our transformers fail, to be more exact, which component of a transformer usually fails and creates havoc. So what we see here is that winding takes 34%, Also, we have 7% cooling, 11 is unidentified components, tanks and accessories, and 20% is OLTC and DTC, which means on-load step changer and the energized step changer. Then we have oil, 4%, core, and bushings. So if you manage to measure the parameters of, let's say, bushings, windings, and on-load step changer, you are already 20, 34 would be 54, 69. So 69% of possible failures you can prevent. So with maintenance and with the right tools and knowledge how to use those tools, you can simply make your transformer live longer. So let us move on and start explaining what are these exact tests which we will be doing. The first is transformer turns ratio. Here you can see the STS, and here you can see some of the accessories you could use to make this testing quicker. It is not necessary. You can do this test even without these accessories, but with these accessories, it is very comfortable and fast to do a test, because with STCS and STCS Plus, you execute one-time connection and you can do many tests. So no climbing the transformer, no hazard for the user or for the person who is on the transformer. Transformer turns ratio, as it is written here, is defined as the ratio of the number of turns of wire on the primary winding, or NP, to the number of turns of wire on the secondary winding, NS. It is the most basic aspect of our transformer, and it basically tells us what is the transformation coefficient, which is actually telling us how our transformer works. So if we have, let's say, 100 volts on the primary, what will we have on the secondary side? So we simply need to divide the number of windings on the primary side with number of windings on the secondary side, which is the same as dividing the voltage on the primary side with the voltage on the secondary side, which is the same as dividing the current on the secondary side with the current on the primary side. Simply observe that this is primary, and this is secondary, because voltage and current have a reverse proportionality when it comes to transformation. So also, turn ratio can be defined as the no load voltage ratio between two windings of a transformer, and that's exactly what we do. We basically generate a voltage on the primary side and we measure a voltage on the secondary side. And excuse me, in doing so, we obtain the ratio, the turn ratio. Now, let us remember one important thing. When doing this test, always generate on the primary side and measure on the secondary. Otherwise, high voltage on the primary side might damage the measurement input. Why is this important to say? If I have a 100 to 10 transformer and I generate, let's say, 100 volts here, I will measure 10 volts here. But if I generate 100 volts here, I will measure 1000 volts here. If my measurement input is not that doesn't have a correct range to measure up to 1 kilovolt, I will burn my input. So for example, on STS, the maximum voltage you can measure is 300 volts, which is more than enough if you measure on the secondary side. But if you measure on the primary side, in that case, you're basically boosting your voltage. You might easily burn the input. And not only that, you can, on the transformer, which is 1000 to 1, if you generate only 1 volt on the secondary, you will get 1000 volts on the primary. So keep in mind, these high voltage can also hurt people. What is the purpose of the ratio test? The purpose of the ratio test is to identify if we have any shorted turns. So for example, you see turns here. Due to high temperature, the insulation between two wires can melt and two turns can shorten. Or you can see if you have any open turns. If you have any open turns, very easy, the current will not flow through that winding, and you will be able to see that when you are executing the test. So this test provides an information on the insulation failure between turns, as we said for this, and it helps us also in identifying the vector group of the transformer. We'll talk about a vector group a little bit later. So here, what we can see is how you actually execute the test. On the device, you will use the 2 kV output. When I say 2 kV output, it doesn't mean you have to generate the maximum, which is 2 kilovolts. you can generate 100 volts, and often we generate between 1 or 200 volts on the primary side. It is not necessary to generate more because the ratio is always the same whether you generate 10 billion or 1. Of course, simply to be sure that we are in a good range, we try to generate at least more than a few percentages of the nominal voltage, but still on a power transformer generating 200 volts is more than enough to measure the ratio. On the other side, we have to measure. So you see that we are measuring on 300 volt input here. What is the secondary side? And we obtain our results. So this is how we do the test. But before the test, what is necessary to know? It is necessary to know what is the type of the transformer. Is it a single phase, a three phase? Is it an auto transformer? The number of windings and phases. So do we have a single phase or three phase transformer? Phase sequence we need to know. And as we mentioned before, the voltage which we are applying on the primary side should not exceed the rated voltage of the transformer. We don't want to damage it. And as mentioned, always to the high voltage side of the transformer. The voltage which is measured must not exceed the measurement input of the voltmeter, as we were saying before, because if we generate on the secondary side, if we measure on the secondary side more than 300 volts, that might burn the measurement input. And what is also important, we often have transformers which have multiple taps, whether they have on-load tap changer or de-energized tap changer, and we should do this on all positions of tap changer in order to get a full overview of our power transformers ratio. So here, if we were to have a single phase transformer, so in some cases we have 3 single phase transformers for, let's say, very high powers. In that case, we have the primary winding and we have the secondary winding, and it's pretty easy to execute this test. This is how we generate, this is how we connect the generation, this is how we connect the measurement. We'll show you later how we set up in the firmware, and we get our result. Then if we have an auto transformer, it is very similar. Again, we generate on, let's say, the whole winding, and we measure from a certain part of the winding as the transformer is set. And because we want to do that on all positions of tap changer, what we will see is a certain, ideally it would be a straight line, but if we don't have a perfect transformer, and let's be honest, very often we don't, we might have something like this, which goes from, let's say, 2.7 until 3.3 as the turns ratio. I'm sorry, I made a mistake. So it is not that it should be a straight line. That was wrong. As we move the tap, we change the ratio, and this is what it is shown. What I meant to say is ideally this should be a straight line. It shouldn't be a curve, and you can see that it's very, very close to a straight line, the one which we have here. So, but if we have a three-phase transformer, then we need to connect all 3 phases. Since STS 5000 effectively has one high voltage output, what we practice in that case is connecting STCS or STCS Plus, as mentioned before, which can then automatically switch from one phase to another and do the measurement for all 3 phases. If we have a 3-phase transformer, the core would look like this normally, and you would have phase A, phase B, and phase C, usually separated like we see in this picture. And then the winding, one would be wound around this core and the other one would be wound around the first winding. So usually inside you would have the secondary, and outside you would have the primary. So this is how you would test your 3-phase power transformer, which would effectively look something like this. And when we have a 3-phase power transformer, another notion which comes to our mind is the vector group. So the vector group is an essential property, as it says here, for successful parallel operation of transformers. So that's one thing why we need to know, because if you have 2 transformers working in parallel, you should know exactly their vector group so that they don't burden each other. When defining a vector group, what is actually a vector group? A vector group is saying what type of winding do you have on the primary side? Is it a Y, is it a delta, or is it zigzag? and what type of winding do you have on the secondary side. Do you have a Y, do you have a delta, or do you have a zigzag? You also need to mention if you have a Y, if you have a Y connection or a star connection, is your star point grounded or not? So in this example, if we have a delta on the primary side, we will say D, and it will be a caps lock. If on the secondary side we have a star, we will say Y, as we can see here. And then N would signify that this star has a star point grounded. Number 11 indicates the difference in phase angle between the windings, between the primary and the secondary side. And because it is taken into consideration like a clock, so you can see this is like a clock, 12 o'clock, 1 o'clock, 2 o'clock, 6 o'clock, 9 o'clock, etc. Every 30 degrees is 1 o'clock. So if we say DYN11, it means that the phase shift between the primary and the secondary side is 11 times 30, which is 330 degrees. So the secondary side voltage is lagging 330 degrees in respect to the primary side voltage. So it is very important to know, and when we are doing a ratio test, it is quite easy also to perform a vector group test. To show you some examples, it is not that there are all possible combinations of vector group available. You can see here that we can have YY0 or YD1, but we cannot have, for example, YD2, because it is not doable physically, it is not a physical reality. So YD, as we said, would mean star delta, and this number is multiplied by 30 degrees to understand what is the phase shift between the primary and the secondary voltage. Here we have DDs, so delta delta, delta Y, delta delta, delta delta, delta Y, etc. And DZ, Z is for zigzag. So these are possible vector groups which we can test. And when we are testing a vector group, we actually need to generate again from the high voltage and measure from the low voltage side. We need to do it 2 tests, twice, and then the STS will give us the vector group of the device itself. So if we have YND11, which means primary side is star, which is grounded, which has a grounded neutral point, as you can see here, and then we have a D on the secondary side and 11, which means the phase shift is 330 degrees between the primary and the secondary. This is how we will connect. So we will connect on phase A and let's say phase R, and then here the same. We will perform 2 tests and we will get the group, the group of the device, the vector group of the transformer. And if we want to do it quicker, as we mentioned before, we can use STCS Plus or STCS. Later we'll talk about the differences, but long story short, it is one-time connection device. You connect the device to STS and you connect the device to the transformer, primary and secondary side, and also the tap changer, which means that you can automatically do a test on all positions of taps, on all tap positions, and on all phases, which makes testing quite faster. Also, you can perform, as we mentioned, the vector group test, and if you're using STCS Plus, we will have 2 more, let's say, smaller boxes to connect, but it makes sense because there is a difference between STCS and STCS Plus. STCS can automatically perform ratio test, winding resistance test, on-load tap changer dynamic test, and vector group test. These are the tests you can do with STCS. With STCS Plus, you can do all this and no load test, short circuit impedance, and important, we have a built-in demagnetizer. So demagnetizer is built in STCS Plus, and with STCS Plus, you can execute 7 types of tests. To be more correct, 6 tests and demagnetization, because demagnetization effectively it is not a test, but still it is an essential thing which you need to perform when after testing winding resistance. So when you would do a test on your STS, this is what your screen would look like. You would have the primary side voltage, the secondary side voltage. These values would be copied from the header the vector group you would write in here, or the system would copy that from the nominal values which you put in, and then you decide which voltage you want to generate on the primary side. 200 volts is more than enough. And if you have an STCS present, then you can also decide from which position to which position you want to go, and do you want to measure ratio on all phases or just one single phase, and in that case you need to choose on which phase you want to do it. When you execute a test, this is another example, you would get a result. So in this case we have a 400 to 143 kV, which gives it the nominal ratio of 2.795. We executed the test here, and what you can see effectively are results. So this is what we wanted to generate, the voltage. This is the voltage that we generated, 201.7. This is the current which was running in the primary side, in the primary winding, and this was the voltage which was measured on the secondary side. By simple division of these two, we get the ratio, and we also get the error. This is important. When we execute a test, you effectively don't need to look at any of these numbers. I mean, of course, it's very good to do that because you will get an idea what's happening, how much are you generating, how much are you measuring. You will see the ratio, but effectively the last row, the last column is what you're looking for. And long story short, golden rule, the number needs to be less than 0.5%. So when doing a ratio test, 0.5% is the maximum error you can have in comparison to nominal values. And when you actually do a test from 17 positions of tap, you would get a result like this. So here, this is actually this test, but this is only one. This was only position 1 on low voltage. Now we have 17 positions here. Of course, we have shown only 3. And here we can see, first of all, how ratio changes from 2.7 until 2.75 all the way to 3.3, which is normal as you change the position of a tap changer. And you also see the error. Now, errors are okay here, errors are okay here, errors are okay here, but this one is not. This is green because in this particular case, because we were testing a transformer which was a demo transformer, let's say we did have an allowance of 1% of difference between the nominal and the measured values, but normally when you're testing your power transformer, 0.5 is the maximum of error you can have, as you can see it here. And another thing which is cute to mention, think about this fact. When you're doing this test, you are generating voltage on the primary side, like this, and on the secondary side, you are measuring the voltage. We know that the voltmeter is effectively an open circuit. It has an infinite resistance. So you could say that the secondary side is open because we have an immense resistance here. So when you look at it, it is like a no-load test, because for a no-load test or excitation test, we generate on the primary side and we measure on the secondary side, with the secondary side open. So this is the same thing, which means that effectively when you do a test and when you look at these currents here, these are the currents of no-load test. Of course, the voltages which you use are much smaller than the ones which were used in the factory when this test was done originally, so you cannot effectively compare the results. But you can do another thing. You can always check if the middle phase has lower current. And you see that it has lower current here. Also, phase B has a lower current here. And also, phase B has a lower current here, which is something which is usually expected when doing a no-load test on more or less a standard power transformer. The second test which we need to do is actually winding resistance test. When doing a winding resistance test, you can do everything with just STS. But any of these accessories would help make it faster or easier. STCS and STCS Plus, because one-time connection is executed. 20 amp DC booster needs to be used with one of these two devices, and it can give you up to 20 amps DC. And then we have a demagnetizer. One thing to mention, winding resistance test is often the last test you do. It is the last test you do because you magnetize the core, and after that, you need to demagnetize that core. Otherwise, you might have issues. But let's go back to the winding resistance test. So as it says, Winding resistance measurement in transformers are of fundamental importance for the following purposes: calculation of the I²R component of conductor losses, calculation of the winding temperature at the end of the temperature cycle as a benchmark for assessing possible damage, and it is done at site in order to check for abnormalities due to broken strands, high contact resistance in tap changers, high voltage leads and bushings in the field, and loose connections. To be practical, often you will be actually looking for loose connections. Basically, you know the nominal resistance, now you measure the resistance, and you don't want the resistance to be higher. If the resistance is higher, then we have loose connections. Or we have broken strands of conductor, then the resistance is infinite. Or if you have on-load tap changer and it is dirty because of arcing and you have some dirt on it, then you will have also a higher resistance on your tap changer. So basically, you don't want the transformer to be overheating because of high resistance, because high resistance would mean that it will be probably that it will tend to overheat. Now, when performing this test, the transformer winding contains both inductance and resistance. What we are saying now is that if we want to measure the voltage drop when we are measuring the resistance of a winding, we need to take into consideration this component, di/dt. How much does the current change? So we want to have a DC current. We don't want to have a current with a ripple, because every ripple is a di/dt multiplied with an inductance, which is not small, because that is the characteristic of a winding, would make the voltage drop quite big. So long story short, this is the longest test because you need to wait for this to become 0. And then when you do a test, basically what you want to measure is just this part here, I times R. This you want it to be 0. So what we do is we generate the current and we wait for the current to reach its static value. It's the value which you set, and then we measure the voltage drop. And in doing that, we can measure the resistance of our winding. So the procedure for a star-connected winding, the resistance is measured between line and neutral, but if we have a star connection of auto transformer, the resistance of high voltage side is measured between the high and the low voltage terminal, and then between the low voltage terminal and the neutral. If we have an on-load tap changer, the resistance shall be taken at each tap continuously without discharging the transformer. If we discharge the transformer, we can do that, but the measurement becomes much, much longer. And if we have a de-energized tap changer or DETC, resistance is also measured at each tap, and before changing, the tap transformer must be discharged. That's the difference between on-load and de-energized. For delta connected windings, of course, we measure between pairs of line terminals. So we measure AB, BC, and CA. So this is what would be the starting rules. And then, as we mentioned before, we require a stable DC source, a voltmeter, an algorithm for stable reading of the resistance, and then we need to also discharge. Discharge is not the same as demagnetize, we'll talk about that later, and then we need to plot the resistance with change in tap. As the tap changes, that's how the resistance also changes. So the connection should be done like this. It looks complicated, but trust me, it's not. What we do here is we generate current, which we also measure, and then we send that current to this winding here, and we close the circuit here. So we just generate current, this is where we generate current onto this winding, and we measure the voltage drop. How do we measure the voltage drop? Excuse me. We measure the voltage drop here. As you can see, the 300 volts measurement point, measurement input is connected also onto this winding, as is the current generation. And then we measure that for phase A, for phase B, for phase C, and we do the same then for the secondary side for each position of tap changer. And if we do it, then it looks like this for all positions of tap changer for 1 to 11, for example. One thing to remember is this test should be done last, not the first. Well, it's not written in stone, but it's most practical because since the test magnetizes the core of the power transformer, if we do some tests after it, for example, like sweep freak response analysis or no load test, we might get, or we will get different results. So do this test last, then demagnetize, and then turn on your transformer again. If we use STCS, once again, one setup is performed, and then we measure for all phases and all positions of tap changer. If we use STCS, it is more a plus, it is more or less the same thing in this case. What we need to mention is how to evaluate the results. So the best is if we have the previous results, the results from the factory, then we will compare all the results, and usually, depending on the country and the region, the difference shouldn't be bigger than 2, maximum 3%. If we don't have the original results, what we need to do is to compare values between phases. They need to have the same value. And again, if the difference between phases is bigger than 3%, in some cases 2%, then we know that we have some issues with that transformer. The new thing in STS, which we didn't have before, is that you can press a button and see actually what is the percentage difference between phases. So this is a new thing we've done. And as you are doing the test, this is what the application would look like. You would say which current you effectively want to use, how much current you want to use. You would need to read what is the minimum and what is the maximum resistance you can measure with this particular current. And then you press start and you get your results here after a minute or two. If you are doing some other tests, here you can see an example of on-load tap changer, which will be our next topic. So talking about on-load tap changer, here we can see again which devices can be used, and they're the same, because when you are measuring dynamic resistance of on-load tap changer, the setup is the same. It's just that the interpretation of result is different, because here you will get a number, and that number, as we said, needs to be compared with a nominal value, or you need to compare phases. So it's a comparison of numbers. But when you do OLTC, you're not just looking at the number, you're also looking at the graph. So let us explain quickly. On-load tap changer is a device which can change the output voltage depending on the load, which is needed from the transformer. If the voltage goes too low, you will change the position of a tap changer, and you will, let's say, compensate on the lost voltage. So what you're doing with this device, you need to have a diverter switch and a selector switch. Diverter switch is a switch which performs the operation of changing, while the selector switch is the part which actually holds inside the different taps. So that's the easiest way how to explain it. So the function of on-load tap changer is to provide a constant voltage to the low voltage winding, and changing of the tap without the energizing of the transformer is the goal. You cannot just interrupt current while the transformer is working, because that would lead to a disaster. Usually, location of the on-load tap changer is in the high voltage winding, because the current in the high voltage is lower than the current in the low voltage, and current is the parameter to take into consideration here. So the number of turns in the high voltage winding are more, so voltage regulation is good, and as we said, the current capacity is less than on the low voltage winding. When you strip naked the power transformer, you will see that it looks like this. It is kind of a device which is encapsulated and connected to all the parts, to all the windings, and it is the only moving part in the transformer, and that's the reason why it, I can't say often, but more yes than no, causes some kinds of faults. So OLTC is quite sensitive. So how does it actually move from one position to another without, you switch from one to another without interrupting the current? How do you do that? This is the procedure. Number one, you decided you want to change the position. And here you want to go from this position here to this position here, from A to B actually. What do? Well, you move the slider in a way that it goes through this, let's say, auxiliary resistances, and from A to B. And this is what it looks like. We follow current. Current is constant here, and that's fine because nothing changed. Then this starts to move. In the next position, since we are now adding a certain resistance, the current starts to go down because now the resistance is bigger. If the resistance increases, the current decreases. In the next slide, you will see that we are now connecting two resistances which are the same in parallel. And because of that, the overall resistance is lower than only the resistance of one of these resistors. That's why the current went a little bit up. You will understand that probably the next step is moving to just this resistor, which would then make the current go even more down. And then slowly we move on to B, where we have now effectively executed the movement from this position onto this position without stopping the current flow, which is the goal. Stopping the current flow is not an option because it would cause a huge issue. Of course, when we connect here, it will take some time for the current to reach a stationary value, but this is not an issue because it doesn't take too much time. Once again, position 1, 2, 3, 4, and then we finish when we get to position B like this. And this is what you will see as we were mentioning the graphical evaluation of the results. And this is what you will see when you are testing. We would define two parameters. One will be called the ripple, and this will be how much does this current change before you start the process of actually switching the positions. And then we have a slope. Slope is how fast this current will change. Here you will see these elements which we've shown before when we are switching from 1 R to 2 Rs and then back to another, just 1 R, one resistor. But what you want to see is that all positions of tap changer have the same outlook, have the same graph. If the ripple or the slope changes dramatically from one to another, then it means that we probably have issues with dirty contacts on our on-load tap changer. So the static resistance provides values of all internal contacts. So all internal contacts of OLTC plus the winding resistance. If you see 1 ohm resistance, it doesn't mean that the winding has 1 ohm. Winding has, let's say, 0.9 ohms, and diverter switch, or to be more exact, the whole OLTC has additional resistance of 0.1. So that's diverter switch, tap selector switch, and internal contacts. That's OLTC plus the resistance of the winding itself. What the ripple and slope provides, so as we said, all internal contacts, winding resistance, which gives us the information on dynamic movement of diverter switch. And also keep in mind that it's always performed for both upward and downward movement of tap position, which is a standard. And in one example here, we can see how from going from position 1 to position 10, the resistance changes from 129 milliohm to 120 milliohm. So effectively, you have 1 milliohm difference. So you see not 129, 128, 127, etc., and 120 is the last one. The ripple is, as we said, this parameter here, and the slope is this parameter here. We see that the ripple is more or less only for position 1. It is different than for all other positions, and also slope is more or less the same apart from position 1. So you can see that all other positions have the same ratio of current change, which tells us that all these positions are correct. I mean, have correct parameters.